Okay, welcome everyone to my continuation of what is linear algebra. Today, one of my favorite algorithms in linear algebra ever, what is Gaussian elimination? It will be about intersections, as we will see. It's really beautiful algorithm. Before we start, it's actually well, this algorithm is kind of well known. It was well known to Chinese mathematicians, whatever, 1,000 years ago, before Gauss ever thought about it. Still, the name Gaussian emulation kind of stuck, and that's what it's called nowadays. So we stick with that. Um, Whatever. The only thing you really need to know is how it works because it what it does because it is really amazing. It's simple and it solves a lot of problems you will ever face in, let's say, in life. Okay, let's just jump right into it. Um, so let's say you have some kind of system of linear equations. And the system of linear equations, well, let's say I have a red equation and I have a blue equation. And each of those equations, it's a pretty simple idea. So you count the number of variables, here x and y. That's the dimension of the space you live in. So let's say R2. And each of these equations defines the corresponding hyperplane in that R2. So for instance, my red equation, you can check that actually defines a line in R2, and it's this line, the kind of diagonal line. And the blue one also defines uh, a line in R2, a hyperspace, a hyperplane. And solving this system of linear equations is equivalent to finding the intersection, so this black point here, of those two lines. There's an equivalent way of writing it in terms of a matrix. The idea is pretty easy. You, 0 and 1 over 2 go here, and you look at the coefficients here, minus 1, plus 1, minus 1, plus 1, 1, 1, 1, 1, and you get a matrix. And you just add a little line here to remind you where the equality signs are. Anyway, each of those system of linear equations defines you this is called a hyperplane arrangement, a kind of hyperplane arrangement. And you look for the common intersection of whatever it is. It might be lines, might be uh, planes in R3 or whatever. And it seems like, at least to me, it feels like a very natural question, how to find this intersection point. From the viewpoint of geometry, this is a really obvious question you would like to ask, a collection of things, and you would like to ask, do they intersect and where? And if so, where? Um, but of course, if you don't would care about geometric interpretations and you just think, I have a system of linear equations given by life, could absolutely happens all the time. How do I solve it? And the Gaussian algorithm is a way to solve linear equations. It's so powerful that you can nowadays feed it into a machine and the machine will solve it in a blink of an eye. But anyway, you can also do it by hand. Maybe not for 500 times 500 system of linear equations, but certainly for those 2 by 2 things I'm showing you, you could do it by hand. And there will be 3 operations, and all of them are extremely natural from the viewpoint of geometry. So no people didn't come up with this algorithm by just let's try something, maybe it works. It's really everything is geometry. And the first operation, geometrically speaking, is extremely trivial. It's a swapping 2-row operation. So each row, so just swap those two, and you see it here. So I just swapped 1 and 2, right? And since each row corresponds to just a line in let's say in this case in R2, and all I've done is basically I swapped the colors of the lines. So this is now the second one, the blue one. The second is the blue one, and this is now the first one, the red one. First is the red one, and of course I haven't done anything, right? So from the viewpoint of the intersection, I haven't done anything. So intersection doesn't change. The next operation is geometrically speaking, even more, it's even easier. It's just doing nothing. And it's just, you can always multiply a row by a non-zero scalar. So don't multiply by a zero scalar, that just will kill the whole hyperplane, right? So, but you can multiply by any zero scalar. So remember that I had a red and a blue one. So I don't touch the red one stays fixed. And I multiply in this example the blue one by -4. Okay, I can do that. I get another system of linear equations, and absolutely nothing changes. So this vector solves the blue equation, and this, so the scale blue equation, and this, the same vector solves the original equation. Really, no change at all, right? So this is absolutely clear for the thing I don't touch because I haven't touched it. Um, and it's also not so hard to see for the other one. So no change at all with respect to actually to the whole picture. So if the whole picture doesn't change, right, then certainly the intersection stays fixed. So that's for sure. So two very easy operations: swapping and scalar multiplication. And the third one, that's geometrically speaking a little bit more interesting, um, but it still doesn't change the intersection. So let's look at it. You can still take the, well, here, the red and the blue row, red and the blue row, and you can decide to add the one to the other. So in this case, so going from here to here, what I did is I took the first and I added it to the second. Okay, so 1 plus 1 is 2. Let's do it. 1, oh, let's do it together. 1 plus 1 is 2. I haven't changed the top one. Minus 1 plus 1 is 0. Okay, 0 plus a half is a half. So I really just added the first row to the second. And what is it doing in pictures? So let's have a look. So here I still have my blue line. That's where I start. And I have my red line. Here you go. Very good. So this was really bad. So let me try again. Really good. And the only thing I do is I take a vector from blue, I take a vector from red, and I add them together. That's what I do. I create a new one by adding 1 and 2. And this is my, whatever it is, purplish vector. It's pointing in this direction. All of you know how that works, right? You kind of fill up. Now my picture isn't all that bad, isn't all that good, but you basically fill up this rectangle thing, and you get a new hyperplane, a new line now going through this vector. So here's now the blue one. But the thing to observe, so the blue one really changes in this case, okay? It's really a different line. The red one, of course, I haven't touched it, it's just the same. But the point of intersection doesn't change. So row plus row doesn't change the intersection. And these are exactly the three operations, the only things you need to remember. So Gaussian elimination is just the process on matrices where you're allowed to swap rows. So that's my swapping operation. You're allowed to multiply rows by a non-zero scalar. Please use a non-zero scalar. Zero is usually a bad idea, but otherwise everything is fine. And you can add one row to the other row. And the really nice thing about Gaussian elimination is, well, here are some properties. For example, you can bring any kind of weird matrix using Gaussian elimination on a staircase form like thing, so some kind of upper triangular form. You can calculate the rank because Gaussian elimination doesn't change the rank. And of course, if you're in the staircase form, you can just read off the rank. And you can solve linear equations, and that's why we're interested in it, right? So if you have a set of linear equations, you do some Gaussian elimination trick, and in the end, you can bring it on this form, where you have just ones on the diagonal and everything else is 0. And of course, now this is easy to solve, right? If you have z equals -1, y equals 3, x equals 2, and you need to solve this system of linear equations, well, there's nothing you need to do. And that's the whole power of Gaussian elimination. It's a very easy process. You only have steps A, B, C, and Yeah, you just do it. Uh, uh, you will always end up by with a matrix that looks like this. You can always just read off the solution to your system of linear equations. And of course, as already indicated here, Gaussian elimination has many more applications. For instance, you can find the inverse of a matrix, and it works as follows. Just take a matrix and you want to find the inverse, and here's the inverse. Of course, I already found it, but let's say I still need to find it. The way that it works is you write M and you write an identity matrix next to each other, and you just divide them by a line, just to remind yourself which one is which, and you perform Gaussian elimination on this matrix. Right? Gaussian elimination just means this set of operations until the M part is an identity matrix, and then whatever is on the other side is M inverse. So this whole thing here is M inverse. Very, very easy. Very, very powerful. Okay, let me summarize. Gaussian elimination is a really, really good, a really, really good algorithm. It's extremely easy, three operations. All of them are completely justified by geometry, and it solves a lot of problems. So it's really worthwhile to look into it. Anyway, I hope to see you next time.